Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Mass Transfer Combined with Chemical Reactions. So, in the first lecture of mass transfer part, what we have seen, if there is a chemical reaction, so then according to reaction type, the contribution from the reaction in the flux has to be brought in differently because of the different nature of the reactions. Because if it is homogeneous reaction, it is occurring in the entire volume. So, then that contribution of the reaction in the mass transfer whatever is there or the flux whatever is there, that should be brought as a kind of source term in the species conservation equation or the balance equation, cell balance equation whatever we do. If it is a heterogeneous reaction, it must be taking place at specified locations like catalyst surface etc. So, under such conditions what happens, the contribution from the reaction in the flux whatever is there, that should be brought through the boundary conditions because it is occurring at a specified location. Since the nature of the reactions are different, they are occurring in different locations, different way. So, then their contribution in the mass flux would also be coming differently. So, then corresponding mathematical representation would also be different. That is what we have seen. So, now what we do, we are taking two different problems. One problem is the mass transfer combined with heterogeneous reaction because that would be simple one. Simple in the sense the contribution from the reaction would be coming into the picture as a kind of boundary condition only. Then second problem we take mass transfer combined with homogeneous reaction where the reaction part is would be appearing in the balance equation, species conservation equation as a source term. So, diffusion with heterogeneous chemical reaction we are taking only the diffusive mass transfer because when you include the forced convective mass transfer combined with chemical reactions, the equations complexity would increase and then you have to go for a numerical solution. So, that is the reason in order to keep the complexity up to tractable level, we are taking only diffusive mass transfer. Consider a model for a catalytic reactor such as shown in below figure in which a reaction 2A tends to B is being carried out. We have a catalytic bed in which gas A is coming in and then that is reacting on the surface of catalyst particles and then product B is forming and then outlet unreacted gas A and then product B are coming out, right. An example of reaction of this type would be the solid catalyzed dimerization reactions which are very common in polymer industries in general. Assume that each catalyst particle is surrounded by a stagnant gas film through which A has to diffuse to reach catalyst surface as shown in figure below that we have in the next slide. So, that is we if you enlarge this catalytic particle. So, if it is a particle, so each particle is surrounded by a gas film, thin gas film. Okay. So, let us say thickness is delta, film thickness is delta, but compared to the radius of catalyst particle, this delta is very small, that is delta is very smaller than r. So, under such conditions what we can do, we do not need to consider the curvature effect and then we can have a Cartesian coordinate representation of these things. Because now this entire all number of catalysts, the complexity of the packing bed etc., all that we are not taking place, all that we are not considering here. We are taking only one catalyst particle on which the reaction is taking place. So, that simple case we are taking. So, now for that we are taking like this. So, if it is a catalyst surface, let us say we locate Z is equals to delta and then hypothetical film boundary whatever is there, that we take Z is equals to 0. Right. At Z is equals to 0, the concentration of A would be maximum, let us say x A naught, and then as it moves through the reaction takes place at Z is equals to delta and then depending on the fastness order of the reaction, rate constant of the reaction. So, then this disappearance, what is the concentration of x at boundary on this catalytic surface, that accordingly that concentration would be there. if it is an instantaneous reaction in the sense instantaneous and irreversible, that is whatever A is there, that is immediately reacting and then forming B within very short time. So, then at the catalyst surface virtually Xa would be 0 if it is instantaneous reaction. We are going to take both the cases anyway. So, whereas the B is very small, at film boundary, that is Xb naught we are calling it. Actually this is forming at the catalyst surface and then diffusing into the bulk gas film like this. So, Xb would be maximum on the catalyst surface and then minimum at hypothetical film boundary, that is at Z is equals to 0, right. So, what is this Xa as function of Z we have to find out, and then we have to find out NaZ also. Okay. The same thing is pictorially shown here. So, since the film thickness is very small compared to the radius of the catalyst particle, curvature effect we are not taking into the consideration. So, hypothetical stagnant gas film edge whatever is there, that we are calling Z is equals to 0, catalyst surface whatever is there, that we calling Z is equals to delta, right, and then the diffusion is taking place in the Z direction. In this representation, x axis is concentration Xa or Xp, and then y axis in the reverse direction is Z, or the vertical direction in the downward is Z axis here. So, now Xa is Xa naught at a hypothetical film which is almost pure, and then it is reacting and then its concentration dropping and becoming 0 at x is equals to delta if it is irreversible and instantaneously occurring, then Xa would be 0 at x is equals to delta, otherwise it has to be represented accordingly. And then this B is forming on the catalyst surface because immediately the reaction is taking place, immediately A is being converted into the B by dimerization equation. So, then it is having profile maximum concentration on the surface x is equals to delta, and then it diffuses back to the bulk from Z is equals to delta to Z is equals to 0. At catalyst surface, assume reaction 2A tends to B occurs instantaneously and product B then diffuses back out through the gas film to the main turbulence stream composed of A and B, and then obtain expression for local rate of conversion from Xa to from A to B when the effective gas film thickness, that is delta, is known, and then main stream concentration Xa naught Xb are known. So, that is Xa naught Xb naught are known and delta is also known. Assume the gas film is isothermal, that is actually not true. Most of the catalytic reactions heat is in energy is involved. So, then there will be temperature difference also, but we are not considering it here in this problem. So, this problem we are taking two cases. First case we take the instantaneous reaction, instantaneous irreversible reaction as stated in the problem. Second case we are taking a reaction of certain order of reaction and then see the solution. But the procedure of getting the solution is same, only boundary condition would be changing. Because why only boundary condition would be changing? Because it is a heterogeneous reaction. So, whatever the changes are there, they are occurring at boundaries only, specified locations only. The case 1, instantaneous reaction. From the reaction 2A tends to B, stoichiometry of the reaction we can get NaZ by 2 is equals to minus NbZ by 1. That means NbZ is equals to minus 1 by 2 NaZ. So, in the combined flux in place of NbZ we can write minus 1 by 2 NaZ like this. Then you take all the NaZ terms one side, then you have NaZ is equals to minus C dAB divided by 1 minus half Xa dXA by Tz. So, now if you have expression for NaZ, you can find out what is Xa as function of Z. For that what we do, in order to get NaZ, we write a balance equation, then we write S multiplied by NaZ at Z minus S multiplied by NaZ at Z plus delta Z is equals to 0, because reaction part will not come here in the source as a source term in the balance equation. It will come as a boundary condition because it is a heterogeneous reaction. It is occurring only at specified location of the catalyst surface. It is not occurring in the film. In the film only diffusion is occurring. Diffusion of species are occurring so that they reach from the bulk to the catalyst surface or catalyst surface to the bulk. Okay. So, now this equation you divide both sides by S delta z and then take limit delta z tends to 0, then you have minus d by dz of NAZ is equals to 0. That means d by dz of NAZ is this one from equation 2 is equals to 0. Now, C dAB we can take constant here, then what we have d by dz of 1 by 1 minus 1 by 2 xa dxa by dz is equals to 0. When you integrate first time, what you get 1 by 1 minus 1 by 2 xa dxa by dz is equals to C1. Now, this dz you take to the other side and then integrate both sides, one side with respect to x, another side with respect to z. Then what we have ln of 1 minus 1 by 2 xa divided by minus 1 by 2 is equals to C1z plus C2. This minus 1 by 2 I can write here as a minus 2 ln 1 minus 1 by 2 xa is equals to C1z plus C2. Two boundary conditions we have at z is equals to 0, xa is xa naught. So, C2 is minus 2 ln 1 minus 1 by 2 xa naught, that is what we get. The other boundary condition, that is at z is equals to delta, xa is equals to 0. Why it is xa is equals to 0? Because the reaction is very instantaneous. The reaction is very instantaneous, that is moment the molecules of A comes and reaches the surface of the catalyst, immediately they are reacting and forming B, right. So, there is no A present at any given time, immediately they are converting into the B because of the reaction. So, that is the reason xa is 0 at z is equals to delta. Z is equals to delta is nothing but catalyst surface location. So, when you apply this boundary condition, you get this one, that is this ln of 1 is 0 and then C1 delta plus C2 is equals to 0, that is C1 you get minus C2 by delta. So, that is this one. So, now you have C2 and then C1, these two if you substitute in equation number 3, you will get the concentration profile. So, this 2 by delta ln 1 minus 1 by 2 xa naught is nothing but C1 and then minus 2 ln 1 minus 1 by 2 xa naught is nothing but C2. These two we can cancel out, right. Then what we are doing from these two terms, ln of 1 minus 1 by 2 xa naught if we take common, we get z by delta minus 1, right, or this both sides if you multiply it by minus. So, ln of 1 minus 1 by 2 xa is equals to 1 minus z by delta ln of 1 minus 2 xa naught. This is the concentration profile. The same thing you can write this way also, right. So, but we need to find out the flux, that is the question. So, then what we have to do, this concentration profile, this equation we have to differentiate with respect to z, then we get 1 by 1 minus 1 by 2 xa minus 1 by 2 dxa by dz is equals to 0 minus 1 by delta ln of this is constant anyway, right. So, that means this 2 also if I take to the right hand side minus 2 by delta ln 1 minus 1 by 2 xa naught I will get in the right hand side. Left hand side I am not doing any simplification and keeping as it is, because flux equation we derived it as NAZ is equals to minus C dAB divided by 1 minus 1 by 2 xa dxa by dz. That means this equation whatever is there, if I simply multiply by C dAB I will get the flux, that is flux is 2 C dAB by delta ln 1 by 1 minus 1 by 2 xa naught. This is the case where reaction is instantaneously occurring and irreversible instantaneous reaction. But in general always we may not have such kind of reaction. So, what we do now, we take a case 2A tends to B is not instantaneous at catalyst surface at z is equals to delta. For that assume that the rate at which A disappears at the catalyst surface is proportional to the concentration of A in the fluid at interface. So, that is NAZ is equals to K1 double prime Ca, that I can write K1 double prime Cxa. This is one of the boundary conditions that we have seen in the first lecture on mass transfer, right. So, here K1 double prime is rate constant for pseudo first order catalytic reaction, right. So, now from this equation what we get? This equation is actually valid at Z is equals to delta, right. So, Z is equals to delta, at Z is equals to delta, NAZ is equals to K1 double prime Cxa, that means Xa is equals to NAZ divided by K1 double prime C. This is the boundary condition. Whereas, the other boundary condition at Z is equals to 0, Xa is equals to Xa naught, that is remaining same, Bc1, that is not changing, right. Only at the catalyst surface, which is at Z is equals to delta. Now, the reaction is not instantaneous, it is a first order reaction as per that one. The flux NAZ is K1 double prime Cxa, and then Xa is equals to NAZ by K1 double prime C. So, in the previous problem, whatever this solving the combined flux equation etc., integrating up to that part, it is same. It is same. The changes whatever is there compared to the previous part of the problem, that is occurring in this problem only from boundary conditions point of view. So, Bc1 is same. So, that is at x is equals to 0, Xa is equals to Xa naught. So, C2 you are going to get the same constant like previous case, and then Bc1 at Z is equals to delta, Xa is nothing but NAZ by K1 double prime C. So, that is we have written here. So, from here C1 you get this particular term. The C2 we have substituted here, and then this ln term also we have taken to the left hand side. So, that all the ln terms are together, and then right hand side we have only C1 delta. So, that delta also if you take to the left hand side, you have 2 by delta ln of 1 minus 1 by 2 Xa naught divided by 1 minus 1 by 2 NAZ K1 double prime C. So, this C1, this C2 you got it, that if you substitute in equation number 3, you will get concentration profile. So, that is this other than Z here in the first term in the right hand side is C1, the second term minus of 2 ln 1 minus 1 by 2 Xa naught is nothing but C2. Now, here also 2 you can take off from both sides, then this particular term you expand it as 2 terms, last term you keep it as it is, and then both sides you are multiplying by minus 1. So, that right hand side we have plus term, and then left hand side all the terms are multiplied by minus. So, this is what you are getting, right. Now, these two terms are same actually similar, right. So, ln 1 minus 1 by 2 Xa naught if you take common, you get 1 minus Z by delta as a multiplication factor, the other term is remaining same, right. So, now all the terms are having ln. So, then these multiplication factors whatever are there you can take as a power terms, and then you get concentration profile expression this one. Now, if the reaction instantaneous, that means K1 double prime tends to infinity, very large. So, then if K1 double prime is very large, 1 by K1 double prime would be 0. So, under such condition this term would be this entire parenthesis term would be 1 minus 0 power something. So, it will be 1 power something. So, it will be 1 only. So, only this part would be there. So, which is the same as a solution of part A, where the reaction is instantaneous. So, if the reaction is not instantaneous and then reaction is pseudo first order reaction, so then this additional correction term will appear in the right hand side. Now, we have to differentiate that concentration profile in order to get the flux equation, because in the flux equation what we have, we have minus dxa by dz terms. So, this is the equation that we got. This if you differentiate both sides with respect to z, what you get? Left hand side 1 by 1 minus 1 by 2 x a minus 1 by 2 dxa by dz is equals to here minus 1 by delta ln 1 minus 1 by 2 x a naught, here 1 by delta ln 1 minus 1 by 2 naz by k1 double prime c. So, the same equation is written here again, and then what we have done? We combined these two terms by after taking these 2 also to the right hand side. So, 2 by delta we are having an ln of 1 minus 1 by 2 naz k1 double prime c divided by 1 minus 1 by 2 x a naught, right. So, now this equation left hand side we are keeping as it is, because this left hand side if you multiply by c dab, then that would be same as flux. So, the same thing c dab if you have to multiply in the right hand side. So, 2 c dab by delta ln of 1 minus 1 by 2 naz divided by k1 double prime c divided by 1 minus 1 by 2 x a naught. Now, here also if the k1 double prime the reaction is instantaneous, so then infinity, then this term again will go to 1, and then solution would be same as a previous case of part A where the reaction is instantaneous. Only thing that k1 double prime would be infinity. So, then 1 minus 0 in the numerator you will be having 1 here if the reaction is instantaneous, which is the solution like a previous one. So, if the reaction is not instantaneous, then this correction factor of this particular term is coming into the picture. So, for large values of k1 double prime instantaneous conversion case, whatever ln of 1 minus 1 by 2 naz k1 double prime c, if k1 double prime is very large, so then this term would be very small. So, ln of 1 minus this term is, we can write 1 minus of that term, right. So, naz we can further simplify like this, then we have this particular term. So, in this particular term after expanding, in place of ln of this term I can directly write 1 minus of that particular term. Then after that what I can do, I can combine this 2c dab by delta terms together, and then we see what we can get. We can get this particular term on expansion, and then all the terms whatever naz terms are there have been taken one side, and then remaining terms are taken other side. So, here again what we can get, naz is equals to 2c dab by delta divided by 1 plus dab by k1 double prime delta ln of 1 by 1 minus 1 by 2 x a naught. If k1 double prime is large, so then this would be 0. So, in the denominator we will be having only 1. So, that is 2c dab by delta ln of 1 by 1 minus 1 by 2 x a naught is the same as a previous part A problem when the reaction is instantaneous. And this dab by k1 double prime delta is nothing but Dam-Kohler number. Now, we take a homogeneous reaction, diffusion with a homogeneous chemical reaction. Okay. Here also we are not taking the forced convective mass transfer, we are taking only diffusive mass transfer, because if you take the forced convective mass transfer, the velocity part would come into the picture, and then the equation will become more complicated. You have to go for a numerical solution. So, in order to have the complexities under the tractable conditions, we are taking only diffusive mass transfer, which is affected by the homogeneous chemical reaction that is simultaneously occurring while the diffusion is occurring. Okay. Consider a system where gas A dissolves in liquid B in a beaker and diffuses isothermally into liquid phase. So, as A diffuses, it also undergoes irreversible first order homogeneous reaction A plus B giving rise to AB. So, irreversible first order homogeneous reaction is occurring. Since it is a homogeneous reaction, whatever the contribution in the flux is there, that should come as a source term in the balance equation, species conservation balance equation, whatever we write. So, the contribution from the reaction has to come as a source term in the right hand side or the third term. And then here A, B and then AB are there. So, it is not a binary system, 3 components are there. So, what we do? We assume this AB is present in very small components, so that we can have a pseudo binary system. Examples where we can have such kind of situations are absorption of CO2 by concentrated aqueous solution of NaOH. Consider this as a binary solution of A and B, ignoring small amount of AB that is formed because of the reaction, that is pseudo binary system. Pictorially, if you see, we have a beaker in which liquid B is there. Now, gas A is coming in and then dissolving here. So, while it is dissolving because of the diffusion, the reaction is also taking place. That reaction is irreversible first order reaction, homogeneous reaction, right. So, now the liquid whatever height is there, that height we are taking L. So, the top location we are taking Z is equals to 0, bottom location of the beaker we are taking Z is equals to L. So, at the top only pure gas A is there. So, at the gas liquid interface whatever the concentration of A is there, that is Ca naught, that is the solubility of A in B, whatever is there, that value, right. And then at Z is equals to L, we do not know how much it is. So, usually that is dou C by dou Z is equals to 0. Now, mass balance on species A over thickness delta Z of liquid phase, if we write NaZ at location Z multiplied by S minus NaZ at location Z plus delta Z multiplied by S minus rate of disappearance of A, that is K1 triple prime Ca S delta Z is equals to 0. Now, this equation here again, if you see K1 triple prime is first order rate constant for decomposition of A, whereas K1 triple prime Ca is the moles of A consumed by the reaction per unit volume per unit time, right. Now, here also what we do, divided by S delta Z, and delta Z tends to 0, limiting conditions you take, minus d by dz of NaZ minus K1 triple prime Ca is equals to 0, that is d by dz of NaZ plus K1 triple prime Ca is equals to 0, right. This we can solve to get the concentration profile, but that you can do only when you know the NaZ expression. So, if concentration A is small, then we can approximate this combined flux NaZ as simply minus dAb dCA by dZ. If Xa is very small, assuming the concentration of A is very small, right, within the diffusing within the liquid system, because we are saying that only small amount is diffusing. So, then this contribution would be very small compared to this contribution. So, we are not considering this part, second part in the right hand side, we are taking only this part. So, Cxa we can write as Ca. So, minus dAb dCA by dZ, that is nothing but NaZ. So, that if you substitute here in this equation, what we have, d by dZ of minus dAb dCA by dZ is plus K1 triple prime Ca is equals to 0. So, that minus dAb d square Ca by dZ square plus K1 triple prime Ca is equals to 0. So, that we can write dAb d square Ca by dZ square minus K1 triple prime Ca is equals to 0. This equation we have to solve to get the concentration profile. Boundary conditions we have already seen, at Z is equals to 0, Ca is nothing but Ca naught, at Z is equals to L, dCA by dZ is 0, or if dCA by dZ is 0, that means NaZ is 0. So, now this equation we are multiplying both sides by L square divided by Ca naught dAb. Why are we doing? We are trying to non-dimensionalize the equation. So, how this L square by Ca naught dAb is coming? So, because this equation dAb d square Ca by dZ square minus K1 triple prime Ca is equals to 0. So, dAb, this Ca, in place of Ca we can have Ca naught, and then in place of Z we can have L square. So, this particular term is having the units of this one, right. So, then inverse of this one, if you multiply then this particular first term would become dimensionless. Same would be true for this one also, right. So, then if we have that one, what will have? Non-dimensionalized parameters we have to find. Z by L we will be writing as zeta, and then Ca by Ca naught will be writing capital gamma, right. So, that is what we are doing now. So, this is the equation, we are multiplying by L square by Ca naught dAB. So, this what we do, we just do it once again so that you can understand clearly. So, this zeta is equals to Z by L. So, that means d zeta is equals to 1 by L dz, and then capital gamma is equals to Ca by Ca naught. That means d capital gamma is equals to 1 by Ca naught dCa, that we are applying. So, now here first we have first term dAB we are having, and then multiplying by L square divided by Ca naught dAB, and then in place of this d square Ca we have Ca naught d square gamma divided by, in place of dz square we have L square d zeta square minus k1 triple prime Ca multiplied by L square Ca naught dAB. This is the other term. So, then what we have? This Ca, what we can write? In place of Ca we can write Ca naught multiplied by capital gamma. So, this Ca naught is cancelled out. Okay. So, gamma L square by dAB is here. Now, here this dAB is cancelled out, this Ca naught cancelled out, L square cancelled out. So, then what we have? We have only d gamma, we have only d square capital gamma by d zeta square minus this term what is having k1 triple prime L square by dAB is there. So, this term we are calling phi square. So, phi square gamma we are having. So, this phi is nothing but k1 triple prime L square divided by dAB under root, or phi square is equals to this one. So, this is nothing but Thiele's modulus, right. So, this equation we have to get the solution. This equation 5 is in this form, d square y by dx square minus a square y is equals to 0, whose solution is y is equals to C1 cos hyperbolic Ax plus C2 sin hyperbolic Ax. So, for this equation 5, similarly solution would be capital gamma is equals to C1 cos hyperbolic phi zeta plus C2 sin hyperbolic phi zeta, right. The same solution is written here. So, now actually this is nothing but the concentration profile in dimensionless coordinates. So, boundary conditions also we have to write in dimensionless form. So, at z is equals to 0, Ca is equals to Ca naught. If z is equals to 0, then zeta is equals to 0, and then if Ca is equals to Ca naught, that means gamma is equals to 1. So, that means 1 is equals to C1 cos hyperbolic of 0 plus C2 sin hyperbolic of 0. That means sin hyperbolic of 0 is 0, and then cos hyperbolic of 0 is 1. So, C1 is 1, right. And then at z is equals to L, NAZ is equals to 0 or dCA by dz is equals to 0. If z is equals to L, that means zeta is equals to 1, and then if dCA by dz is equals to 0, that means d gamma by d zeta is equals to 0 in dimensionless form. That means you have to get what is this d gamma by d zeta. So, d by dx of cos hyperbolic x is sin hyperbolic x. Similarly, d by dx of sin hyperbolic x is cos hyperbolic x. So, C1 sin hyperbolic of phi zeta plus C2 cos hyperbolic of phi zeta. Now, zeta is equals to 1, you have to substitute here because it is true zeta is equals to 1, right. So, that is C1 sin hyperbolic of phi plus C2 cos hyperbolic of phi is equals to 0. That means, C2 is equals to cos hyperbolic of phi is equals to minus C1 sin hyperbolic of phi. The C1 is 1. So, that is C2 is nothing but minus tan hyperbolic of phi. Okay. So, now you have C2 and then C1, those things if you substitute in this equation, you have the final solution. So, C1 is 1, C2 is minus sin hyperbolic phi by cos hyperbolic phi. We are not writing as tan hyperbolic of phi for some reason. So, then what we do? Now, you do the LCM. So, then you have this one. So, now this is cos x cos hyperbolic of x cos hyperbolic of y minus sin hyperbolic of x sin hyperbolic of y is nothing but cos hyperbolic of x minus y form, right. That means, you get gamma is equals to cos hyperbolic of phi minus phi zeta divided by cos hyperbolic phi is as it is. So, that is cos hyperbolic of phi of 1 minus zeta by cos hyperbolic of phi is the concentration profile in non-dimensional form, right. Thus, the final solution in dimensional form would be in place of phi you write square root of k1 triple prime L square by DAB, in place of zeta you write z by L, and in place of capital gamma you write Ca by Ca naught. So, Ca by Ca naught is equals to cos hyperbolic of square root of k1 triple prime L square by DAB 1 minus z by L divided by cos hyperbolic of square root of k1 triple prime L square by DAB. So, now we wanted to find out the average concentration. So, this average concentration, if you do Ca average by Ca naught, it will be integral 0 to L Ca by Ca naught dz divided by integral dz, limits 0 to L. If the same thing, if you write dimensionless form, Ca by Ca naught is gamma, dz is nothing but L d zeta. Integral limit should be 0 to 1. If L is equals to 1, that means zeta is equals to 1, right. Similarly, here also we can write the same thing, the limit is 1 here, here also the limit is 1. So, this L you can cancel out, right. So, now you do the integration of this particular term divided by integration of d zeta is 1, limits 1 to 0. So, it is 1, and then integration of cos hyperbolic of x is nothing but sin hyperbolic of x. So, that is sin hyperbolic of phi of 1 minus zeta divided by minus phi, and the limits 0 to 1, whatever divided by cos hyperbolic phi is the constant as it is. So, limits 0 to 1 if you substitute sin hyperbolic of phi of 0 minus sin hyperbolic of phi of 1. So, this term is 0, and then this sin hyperbolic of phi divided by cos hyperbolic of phi is tan hyperbolic of phi, and then this divided by phi is as it is. So, then Ca average by Ca naught is nothing but tan hyperbolic of phi divided by phi. So, if you replace phi by square root of k1 triple prime L square by DAB, this is what you have the equation. This is the equation for the average concentration, right. Now, the flux, if you wanted to find out this, whatever the Ca by Ca naught expression that we have in the previous slide. So, that we have to differentiate with respect to z. So, then d by dz of Ca by Ca naught is 1 by Ca naught dCa by dz, and then d by dz of this entire thing. This is anyway constant. So, this is as it is, and then d by dx of cos of hyperbolic x is nothing but sin hyperbolic of x. So, sin of h square root of k1 triple prime L square dAB 1 minus z by L, and then differentiation of minus z by L square root of k1 triple prime L square by dAB is nothing but minus 1 by L square root of k1 triple prime L square by dAB. So, this Ca naught in the left hand side, that we take to the right hand side, and then wherever this square root of k1 triple prime L square by dAB is there, that we are writing phi. So, minus Ca naught phi by L is this term, sine hyperbolic of phi 1 minus 0 by L, because this we are now doing at z is equals to 0. The flux we are calculating at z is equals to 0 location, that is at the interface, gas liquid interface. So, if you substitute z is equals to 0, this sine hyperbolic of phi you get. So, sine hyperbolic of phi divided by cos hyperbolic of phi is tan hyperbolic of phi, right. So, this term both sides if you multiply by minus dAB, you will be getting the flux, because NAZ is equals to minus dAB dCA by dZ at z is equals to 0 is equals to Ca naught dAB by L phi tan hyperbolic phi. That if you write in terms of dimensional coordinates, so then we have Ca naught dAB by L square root of K1 triple prime L square by dAB tan hyperbolic of square root of K1 triple prime L square by dAB as the flux that we supposed to find out. The references for this lecture are provided here. Of course, both the problems you can find out in this book, Transport Phenomena by Bird, Stewart and Lightfoot. Thank you.